Hello and welcome back to Trigonometry, MAT 155. In this lecture, we're going to be discussing the basics of vectors. So, in simple terms, so when we're starting to define a vectors, we want to do so sort of geometrically. And when we talk about it, we just want to think about a vector as an object that has both a magnitude and a direction. And this is compared to just a number like you're used to dealing with. We just call that a scalar, which only has a magnitude. Okay, so what is it? More precisely, it's a directed line segment that has an initial point. Line segment means it stops at both ends. So it goes basically from an initial point to a terminal point. And that distance, we call that the magnitude. And the length of which is the length of the segment. And the direction is basically where the arrow points at the terminal end. We'll often give it names such as V, and that's bold here. It's hard to kind of bold in writing, so a lot of times in writing people will just put like an arrow. Sometimes people a little hat, which we'll see later on in the lecture. But what can we do with vectors? Well, we can add them. We can subtract them. We can multiply by constants. We can't necessarily multiply the vectors sort of traditionally. There are some things we can do, but that is for a different section. Or a combination of all those. It doesn't have just to be two. We could do it with multiple vectors as well. So let's first start talking about geometrically what it means to add them. And when we're adding vectors geometrically, we take one of the vectors and we put the tail of the one we're adding to it at the head of the other, and then just preserving the direction and the length of it. Okay, and then we draw a new vector from the tail of the one that we started at to the head of the one we're finishing at. And that new straight line vector is called the resultant. Basically, it just means the final or the output vector. Because its initial point is where we started the first, and the terminal point is where we ended at the second when done this way. So let's take a look at an example. So if we start with these vectors, so we got a vector starting here and going this way, so we can see that, hey, it goes right 3 up 2. And then we got another vector that goes right 2 down 3. So we can just do the same thing. I'm just going to kind of start from the middle, see what happens. So we're going to go right 3 up 2, right 3 up 2. Draw this vector. So this was V. It's hard for me to put bold, so I'll put the little arrow over it. And then W is right 2 down 3. So right 2 down 3. And it looks like this. So these two vectors sort of combined make this new, and we'll call this one the resultant vector. I'll put it in black just to at least distinguish. Assuming I can get ink out of this. So with this new vector, I'm going to give this one the name W. Put a little arrow next to it. Again, it's hard to bold when just writing, so a lot of times it's easier just to put the arrows. But we get something like this. And this new vector right here is the resultant vector. Okay? It's what we get out as the answer. Okay, so a couple things to note. So we don't want to live in geometric land very long. It's not all that much we can do with it. It's best saved for stuff like free body diagrams for physics, which I will bring back up in a little bit. But really, it's mostly to get an idea. And we can note a couple of things from here. One, so we need a magnitude and we need a direction, which we kind of get both in both of these. So what can we say? Well, we can really just think of the vectors as starting from the same place because or we can really change where we think about them as starting, because it really doesn't matter, okay? And we really want to know just how far left to right or up and down we've gone as from the resultant vector when we add or subtract or scale it by 3. By the way, subtraction, you would just flip it and then go the other direction. So it's like adding a negative is what's really going on with subtraction. So this leads to the idea, since we're just telling how far left and right or up and down we're going, that this resultant vector went right 1, 2, 3, 4, 5, and it went down 1 from the original starting point. So we got an idea of what happened with the vector, what the vector looks like from the original starting point. And so we can then define a vector in a different way, less geometric and more sort of with more numbers. And we call an algebraic vector something that describes the vector as if it were at the origin and going in the direction in the components of the vector. So not actually saying it's actually at the origin. We're just saying, hey, wherever we're starting from, go this direction, okay? So, and we give it by, so we denote this new vector, v, by these little braces, because it's not a point. So as we're talking about going left and right, up and down, you might think it's like an x and a y, but it's a little different, because again, we have the whole segment and we have the direction. So we give it these little brackets to distinguish between a point. And a and b are just real numbers. And to be clear, there's another idea. These, by the way, the a and b are called components. But there's a kind of a competing idea called the position vector. Sometimes we may just kind of throw these interchangeably, even though they're technically not. But a position vector does assume that it starts at the origin. So the minor differences of the algebraic vector, again, they would both be represented exactly the same way. It's just in the nuance of what you said, hey, where this actually starts. So again, we're pretending as if it is for the algebraic vector, and it does actually start at the origin for the position vector. That's the difference. So precisely, a position vector is a special kind of algebraic vector, but it wouldn't really be noticed. So again, we would still write it the same way. So, and again, why do we say this? Well, position vectors a lot of times specifically will kind of throw it at an origin that we've made ourselves in physics or in engineering when making free body diagrams, when we actually want to draw these things to get an understanding of what's going on. It just makes those problems particularly easier. But so let's actually go through and find an algebraic vector that has an initial point of 4, 3. And has a terminal point of 1, 7. So 4, 3, that's the initial point. And then a terminal point of 1, 7. So 1, 7. So all the way up here. So that's the vector geometrically. And what did we actually do? Well, we went left 3. So we kind of went... we can call it V, a little arrow to indicate we're dealing with a vector. Went left 3, so we kind of think about going right as positive, left as negative. And then up from the initial point, 1, 2, 3, 4. Okay? And if you only had the points, you didn't actually just draw it and could count, how would you do it? Well, it's just a change in y over change in x. So or not changing y over change in x, just change in x and then change in y. And this means that you have to do what's called the final minus the initial. So the final x minus the initial x, and the final y minus the initial y. So we would do 4 minus 1 for the x's, and then 3, oops, I did this backwards. Final minus initial. Not the initial point was, sorry. The initial point is 4, 3. So we would do 1. It's our initial point minus, and our final point is 1, so minus 4. Excuse me. And then our final point is 7 minus 3. 7. Our initial or final y is y component is y. Our initial y component is 3, and we would get the exact same thing: negative 3, comma 4. two different ways to think about it. One's more geometric, one is more algebraic, but however you decide to do it, you can. This way is a little bit more precise because sometimes the geometry doesn't always work. These don't have to be nice numbers. They could be decimals, they could be decimals that go on forever rather than just finite ones, but we could have something like this. And then one more thing. We can also talk about the idea of sort of the magnitude of a vector. So again, I said it has to have a magnitude and a direction. So the magnitude of a vector is given by this little notation. It's got like two little bars around whatever our vector is, so we call it v. And what we do if a v is defined with AB, basically how long is this line? This is just if we look at it like this, just like we did with the complex numbers, it's just a triangle. So we can talk about the legs, which really these kind of are like the legs, except they can go in negative directions, right? And square them, add them together, and square root. So it's just the Pythagorean theorem. So let's compute the magnitudes of the following. So v is -3, 4, like we had there. Then what we can do, we're trying to compute this. It's the square root. And again, write it the way that I can easily write it. -3 quantity squared plus 4 quantity squared. And we get, in this case, -3 quantity squared is +9. 4 squared is 16. And we get 9 plus 16 is 25. And we get out 5. So the magnitude of our vector v, in this case, in the case that we had up here, in this case is just 5. Okay? It doesn't have to always be nice numbers. So for example, if we're trying to find the magnitude of w, well, again, let's write it out. Was the square root of 7 squared plus 3 squared. Just put parentheses just to be extra safe here, even though we really don't need it since they're positive anyways. But 7 squared is 49. 3 squared is 9. And the square root of 49. And 49 plus 9 is 58. And we can't simplify this square root. You could find a decimal approximation, but with the square root, that is an exact answer. And that's what we'll leave it as. This concludes the lecture on basics of vectors.